Hello folks, this is Doug, and in this video we're going to quickly talk about what the Williamson ether synthesis is. It's really just kind of a fancy name for something that we've more or less already been doing, and so we're just going to put concepts that we've already learned together. So first I want to review some ways that you already know how to make alkenes. You likely have already done some alkene reactions before, maybe you haven't, but if you have, right, you learned that you could do things like take an alkene, right, and add water. That would be regular hydration with like a catalytic amount of acid, and that you ended up adding an OH to the more substituted carbon and an H to the less substituted carbon. Now you can do the exact same thing if you just switch out your water with an alcohol. Say we use ethanol. It does the exact same mechanism. It's nothing different. It's just that now you're going to add an ethoxy group instead of an OH group. So I put hydration in quotes because it's not really, you're not really adding water, but you just do it with an alcohol instead and you make an ether, right? In this case, I have an ether. But it's the same mechanism. We've also seen, right, that we can do this with SN1 reactions, right? So if I take, I'll use a similar looking molecule. Actually, let me go back to black here. Right, if I had this molecule, bromine, I can just add whatever alcohol I want, and all this can really do here, right, is an SN2 reaction, or sorry, SN1 reaction, because I've got a poor nucleophile and a tertiary alkyl halide, and so you'd end up getting products, right, that are ethers, where the bromine leaves, cation forms, and this alcohol adds, giving you, I had a propyl in this case, that molecule, which again is an ether. So we've probably seen examples like this before, but not really thought about it in terms of ways to make ethers. Similarly, right, SN2 reactions, you've done a lot of SN2 reactions. So if you have some sort of alkyl halide, and maybe you have, let's say CH3 O minus, and I'll put sodium, let's say it's sodium methoxide, right? We know that this can just do a backside attack. We've got our good old SN2 reaction. I don't even draw the arrows for this one, right? Backside attack to give us this. But again, this is an ether. And so we haven't really thought about the fact that we've been making ethers. We've been thinking about them in terms of, oh, is this SN1, SN2, etc. So the Williamson ether synthesis basically is this SN2 step, right? This is a Williamson ether synthesis. What we're going to talk about in the next slide here is that the big difference that makes it the quote-unquote Williamson ether synthesis is that how did you make this alkoxide? Usually it's a two-stepper where you make the alkoxide, then you do the SN2. So let's look at this, right? So classically, the Williamson ether synthesis is two steps. One, first you have to deprotonate the alcohol because the idea is that you need to make the alkoxide, right? The idea is to make the alkoxide. Right, which is our good nucleophile. And so you're going to do that by doing something like either you'll have, I'll just use propanol here. You're going to do it by adding some sort of stronger base that's not going to really get in the way. So NaH is a good example because it's going to just simply deprotonate your O minus, and the H minus, the hydride, is going to attach to the proton on your alcohol to give you H2. And then your sodium is going to hang out, and lo and behold, you've made your sodium propoxide, which you then could use as a nucleophile. The other way you're going to see, aside from NaH, is sometimes you'll see people just use an alkali metal itself. So just like sodium metal itself. And I put that 0 there because that's supposed to be the oxidation state of 0, or you might see a solid symbol written afterwards like Na and then in parentheses S. And then that does more of a redox reaction, but it functionally gets you the same thing, only you don't have H2 as a side product. Or actually, you do have H2 as a side product, sorry. And what's nice about having H2 is that it's a gas and it leaves. The only thing you got to be careful with when you make H2, right, is that it's super flammable. And these are exothermic reactions. So you want to make sure things are well ventilated and that you're being safe. But so those are the two ways that we would deprotonate an alcohol. Either use sodium metal or sodium hydride as a good base. Then your second step here is to add some sort of alkyl halide to do an SN2 reaction. Right, and since we're doing an SN2 reaction, really the only alkyl halides that you can use here are either methyl or primary alkyl halides, right? Because you need that unhindered substrate so you can do that backside attack. So that means, and I'll put this, this is an important point, this does not work with secondary or tertiary alkyl halides. Right? And it's just because those are going to give you more E2 product than they're going to give you SN2 product. So this goes back to everything we learned about SN1, SN2, E1, E2, right? If you have a substrate that's secondary or tertiary, it just slows down your SN2 so much that E2 tends to predominate and outcompete. So those are the two steps of the Williamson ether synthesis. Now, if I look at this example below, how would I apply that to this, right? So I'm starting off with my alcohol. I'm ending up with an ether. I see that really the difference here is that I've added this piece, this ethyl piece. So I need to get that ethyl piece. And I know that that is going to come from the alkyl halide. That's going to be the second piece that I add. So I'm thinking, it's going to be like, maybe I'll put a bromine on here, something with a good leaving group. And actually, now that I'm saying this, I say alkyl halide, but it could be like, you could have a tosylate or triflate or something like that on there instead. Just something with a good leaving group, something that's a good SN2 substrate. So what I would do here then, if I wanted to put in what reagents I want to use, first I got to deprotonate it. And so that means I'm going to choose either NaH or just straight up sodium metal. I'll choose NaH this time. And what that's going to do, right, so I've got my hydride, I'm going to treat it like I do any other alkali thing. I'm going to basically split them up. So my hydride is going to pluck off the hydrogen. I don't see that bond, but there's the bond, the OH bond right there, right? And that's going to give me my alkoxide, O minus. It gives me H2, right, which again is a gas and just bubbles away. Now sodium's hanging out next to that minus. And so that was my step 1 stuff. And then for step 2, what I'm going to do is I'm going to add my alkyl halide. I'm going to add my ethyl bromide, or my bromoethane. And so then for step 2, right, I've got this piece. Now we're just going to do the good old backside attack to give us our product. And then as a side product, right, you'd have sodium bromide or NaBr floating around, sodium ions and bromine ions floating around. So that's really what the Williamson ether synthesis, I have trouble saying that sometimes, is all about. It's always 2 steps, 1 and 2. First step is deprotonate the alcohol. Step 2 is add that good SN2 substrate so you can make your ether. So let's look at some examples. So here, right, step 1, right off the bat, I'm saying add NaH. So now I know that this molecule becomes O minus. And then I have CH3Br. So I know that this is going to attack the back of that carbon-bromine bond to give me OCH3. All right, that would be my major product. Notice that I didn't have any inversions of stereochemistry or anything like that. I never broke that carbon-oxygen bond, so I'll even make a note of that here, right? Did not break that CO bond, so I didn't change the stereochemistry there at any point. This would be a good point, right, to stop and take a stab at these last 3, right? So I have 2 more. One to just tell me the product. The third one is, well, what reagents would you add in order to get that product? And then the last question is just asking you, what is the best way to make methyl T-butyl ether using the Williamson ether synthesis, right? So if you had to make this ether, what would be a good way to do it, right? Really, there's 2 options. One is great, one is terrible. So go ahead and pause, take a crack at these last 3. All right, hopefully you had a chance to pause there. For this second one, right, the sodium is going to do basically the same thing that the NaH does, the sodium hydride. It's just going to give you an O minus, right? It's going to take away that hydrogen, turn it into hydride or H2 gas. And then step 2, I have a iodo-propane, and so we're going to do the SN2, right? It's a primary alkyl halide. And I'm just going to replace the H on the O with 1, 2, 3 carbons. And like I've said before, if these are always count your carbons. It's a good idea to label them, right? Just to make sure that, okay, I needed to add 1, 2, 3 carbons. I added 1, 2, 3 carbons. But you didn't actually miss anything. So that would be the product for the second one. For the third one, I need to come up with, well, what do I want to do for step 1? What do I want to do for step 2? And so for this one, it looks like, right, I got a T-butyl group, I got a T-butanol, and then I've got a T-butyl ether with this other new thing here. So this must be the piece that I'm adding in the second step as alkyl halide, right? Because the piece on the left, that's my T-butyl piece. So for step 1, I just got to pick a way to deprotonate it. I'm going to choose just the sodium, the metal one, which is the Na with the 0. Again, you might see an S written after it to indicate that it's a solid, not that it's the ion. It's not Na+, it's Na0. And then for the second step, I'm just going to draw that whole piece with my halogen coming off, and I'll pick bromine for this case. I'll pick bromine. And again, just to make sure I've got enough carbons, 1, 2, 3, 4, 1, 2, 3, 4. Looks like I'm all good, right? I should have that methyl coming off of 3. The point of attachment, the place where I want the bromine is on carbon 1. Looks like I'm all set. Now for this last one, right, we've got 2 different ways to make the Williamson, to make this ether using the Williamson ether synthesis. I can either start with methanol, and then do step 1, something like sodium hydride, and then step 2, use the T-butyl bromide. Or I could have started with the T-butyl alcohol. Step 1, I'll just use the same base. And step 2, use the CH3Br. Right? And so why would these really be different? In theory, they should be kind of similar-ish. In both of them, you're going to make your alkoxide. And the second one, you're adding an alkyl halide. But remember, right, we said that the big issue here is that the second step has to have a good substrate for SN2 reactions. For this one with that T-butyl bromide, this is tertiary, which is going to go E2. It's not going to go SN2. In my second one, this is methyl, which can only do SN2, which is exactly what I want. So the second one would be a much better way to make this ether, right? Using the Williamson ether synthesis, much better way. The other way would just go E2 and you'd end up with an alkene and methanol, which is obviously not what you're trying to make. So there are if you're being asked to make an ether, just pay attention to that exactly, right? Make sure that the second thing that you attach, right, that alkyl halide, that it's a good SN2 substrate, and you should be good. So that's what the Williamson ether synthesis is. Do some practice. Let me know if you have any questions. Study up. Good luck.